Hello students, I am Dr. Tanmay Vishwas. I welcome you all in my channel Chemistry, the Mystery of Molecules. I know after a long days I am in front of you in a face-to-face interaction and I am highly obliged to have it. So let's start. I hope you all are quite well. I don't say very happy because I know the situation. So we have to be happy and we have to maintain our physical as well as mental stability. So let's start. So today we will discuss a very basic question, or rather than it's a confusion. Okay, so it's a confusion that which is more accurate, heat of hydration or heat of combustion. So this thing we will discuss and few points we will cover during today's discussion, that which method is universal to consider or conclude about the stability of an organic material, point number 1. And second, we will discuss a little bit about mechanism and finally few examples. Okay, so today's discussion will be mainly qualitative such that your basic idea gets cleared. So let's start. First of all, so as you can see from the term heat of hydration and heat of combustion, heat of hydrogenation means, for example, you have an alkene, this, and you reacted this with hydrogen in presence of transition metal catalysts like nickel, palladium, platinum, etc. And remember, all these are in zero oxidation state because I'll explain a little bit, but these low valent metals, but to say near about noble metals helps in hydrogenation. And what it results? It results in a alkene. For example, if you take this is R CH2 CH3. Okay, and along with that what happens? Some amount of energy comes out. Why energy comes out? See, in this case there was one pi bond. So one pi bond, and this pi bond is converted into 2 sigma bond. So if I write it in a better way, then you can understand this and this, and these 2 hydrogen came from this. So in expense of 1 CC pi bond, what we are getting? 2 means in expense of 1 CC pi bond and 1 hydrogen sigma bond, what we are ultimately getting? This carbon hydrogen 2 sigma bonds. Okay, so this is the main change, and for that reason some amount of energy is released. Actually better to say energy released. So consequently, what is the value of delta H? Delta H is negative. Okay, I am not doing quantitative, it's negative. So some amount of heat is coming out, and that is called heat of hydrogenation. Basic molecular level point of view, if we want to understand what's actually happening, see this CC pi bond, these pi bonds are formed by the sidewise overlap. Actually I am considering this is pi, that's why same symmetry. So this is the sidewise overlap. Okay, sidewise overlap between the involved p orbital, and the electron density remains in this zone. So this one carbon, this one, so this area. Okay, so it is not exactly in middle of these 2 nucleus, because this nucleus are positively charged, and electron, when these 2 electron remain in between the 2 nucleus, then they are highly stabilized because they got directly attracted by the nucleus. Okay, so if we consider, so this is movement towards stability. Okay, so stability. Now we understood that these pi bonds are slightly less stable. Okay, slightly less stable. I am not saying it's unstable. Don't get confused. And this is actually a sigma bond. Okay, in this case this is sp3 bond, means this is one sp3, this is one hydrogen. Okay, so that's why they are more stable, because if you look at this, the electron cloud is in this region, okay, in between the 2 nucleus. That's why this is more stable. So this is the fundamental about heat of hydrogenation. Okay, now this we understand, and little bit about mechanism as I told. So if we want to understand the mechanism means how the reactions are happening. And by the way, for that purpose I am just focusing on any, and generally this nickel is better to say Raney nickel. Okay, we will discuss some other day about Raney nickel. At this point just understand this is a highly porous nickel, absorb huge amount of hydrogen gas inside it because this is prepared from a 50-50 nickel aluminium alloy. So 50-50 nickel aluminium alloy, and during the reaction the aluminium means this alloy plus sodium hydroxide, if you react, what it does, it produces sodium aluminate plus hydrogen, and nickel doesn't react with NaOH, and this hydrogen is absorbed on nickel. So that's why first of all porous. Why? Because you are roasting an alloy. Second, this hydrogen is adsorbed on this nickel. That's why this is hydrogen rich and it is capable to execute the hydrogenation reaction. But just not this. So what happens in this case? Actually, or better to say, if you consider palladium, what happens? Because this is most wide, generally it's highly used. This is the heterogeneous catalyst bed palladium. So when you react this with hydrogen, what happens? It undergo, this palladium is in zero. Oxidative addition means this hydrogen kept this means this hydrogen is -1 and palladium is +2. In this way you can understand. What happens in next stage? Next stage, this alkene. Alkene goes and again sits on this catalytic bed. Why? Because remember, this palladium, such kind of metal, can donate electron, can withdraw electron. Its energy levels means orbital can make a good overlap with this alkene, hydrogen, this thing. That's why they are chosen. So this you may consider in this way coordination. This hydrogen, again one hydrogen shifted. So what it result? You may consider that this is the one hydrogen. Just consider in this way. One hydrogen, in second another hydrogen is left, and this is actually reductive elimination. Means this whole part eliminates, and what it results? It results this hydrogen plus the catalytic bed regenerates. This is now again palladium 0. At this situation also this is palladium 2 plus 2. Okay, so this is the overall mechanism of this process. Now, so this is the thing we understood. Now the second part of our discussion, that is combustion. What do we mean by that statement? Combustion means that burning of any hydrocarbon in presence of oxygen. Okay, so what happens? For example, let's consider this R equal to CH3. Then what we are taking? We are taking CH3, CH double bond, CH2. This is a propane. If you react this with oxygen in presence of either heat or HNO, both possible. So what it resulted? It resulted in carbon dioxide and water. Okay, so common thing. The stoichiometry between the carbon dioxide and water may change, but the rest of the things are completely common. And in this case also, some amount of energy released. So, okay, so this is also energy released. In both cases, energy released. Why? See, again a pi bond converted into carbon oxygen. You will say that, sir, there is also pi bond. How can you say that this is more stable? See, in this case, there is a carbon-carbon pi bond. In this case, there is a carbon-oxygen. So, point number 1. Second, this reacts with this oxygen. See, oxygen, if you look at its molecular orbital, it is actually a diradical, 2 ampere electron. It is not actually this. This is, remember, this is singlet oxygen, and this is highly toxic. In atmosphere, this is not the major product. This diradical thing is major product. There are some dyes like rose bengal, those things, which can convert these into this, but that's not a very natural thing. So what happens? This is actually, you can consider that this is actually the oxygen available into the atmosphere. So it is not that much stable, sir. It's a highly electronegative atom. So electronegative atom prefers to form bond with electropositive atoms such that it can get stabilized, and that is exactly happening in the case of this carbon dioxide molecule. Carbon is relatively less electronegative, oxygen is more electronegative, so their bonding is better. Fine. Second, there is a water formation. This is the main important factor. Why I am saying that? See, oxygen is in -2 oxidation. In this case also -2, but in this case also -2. So in both cases it getting stabilized. Okay. So this is now if I want to balance the equation. Now see, there are 3 carbon. How many number of carbon? That many number of carbon dioxide. Fine. Now if we want to make 3 carbon dioxide, fine, means that's okay. And another thing, source of hydrogen is this. So here hydrogen, 3 plus 3 6. So what we can expect? We can expect 6 means 3 water. Now based on this in this case 3 oxygen, in this case 1.5 oxygen, not possible. So that's why what will happen? You can multiply everything to, sorry, later we will put, in this case it should be 6, in this case it should be 6. So right now 3 3 6 12, this is 12. Now oxygen, carbon also 3 multiplied by 2 6. Now look at oxygen, 6 molecule oxygen here and 3 here. So here the number of oxygen required is 9. So this is the balanced equation. So everything we understand about the process. Now question, which is better to conclude? Frankly speaking, both are good at its own place. But now we have to conclude that which one is better compared to each other. Okay. Now just a very interesting point you can observe here. In case of hydrogenation, if you take different precursor, different product may produce, may not produce. There is a confusion. But if you take any alkene, means any hydrocarbon, and burn it in presence of oxygen, ultimately it will result in carbon dioxide and water. There may be difference in carbon dioxide number and water number depending on the carbon and hydrogen present in the molecule, but end product is same. Okay, so now just understand this thing little carefully. For example, you have taken, this is CH2, CH, this is actually 1-butene. Okay, and you reacted this with hydrogen in presence of catalyst like palladium. I am not going. So what it will you will get butane, fine, plus energy delta H. In this case delta is also negative, that's fine. Now another thing, if you take this and if you react this with hydrogen similar, what you will get? Again butane plus delta H1 you can consider. Okay, so based on this delta A, this and this difference, you can conclude which one is more stable. You have got it? Fine. So in this case we can make it. But if I say another isomer of butane, that is butene, better to say, this plus hydrogen, what is the product in this case? In this case product is this isobutane. Can you in this case also delta H? So delta HI. Now question is, can you compare these three? Obviously no. We can compare these two because the end product are same. Look at carefully. That's why we can compare. But if the end product is not same, how can you compare? Okay. Now you may confuse, what are you saying, sir? For that reason, let's give another kinds of operating. What do I mean by the statement? Let's draw this energy axis. Fine. And here is your, say, 1-butene. Internal alkyne we consider more stable. Okay. So that reason I am considering here 2-butene because of more hyperconjugation available now. Fine. And through a something transition state they are converted into same product. Okay. So in this case, so for example this is this, I am not going anything this. doesn't matter. Ultimate matters is that sorry, I made little mistakes. Okay, this. Now, question is, how much stabilization? In this case, this. So, one case delta H1, another case, this is delta H2. So, in this case, we can do, but can we compare this thing with isobutene? Not possible because product is different. Okay, so what information I have given? Here again, if you want to compare this versus this, which one is more stable? Can we get using heat of hydrogenation experiment? Obviously, because if you do the heat of hydrogenation experiment, ultimately both will result. Ultimately, at the end, both will result this cyclohexane. Possible, but in this case not. But so we have understood, if the ultimate product is same, we cannot explain that thing completely with heat of hydrogenation. But in case of that, this and isobutene, if we compare, ultimate case, number of carbon and hydrogens are same. Okay, in this case, so number of carbon dioxide produced will be same, number of water produced will be same, and difference will be where? Based on the energy, because the energy of starting material, because at the end, carbon dioxide and water, fixed product. If you take the same stoichiometry, means same molecular formula, means carbon hydrogen ratio same, then ultimately number of carbon dioxide and water will be same, so ultimate energy output will be same. So based on that, you can simplify the complicated situation like this isobutane arises in case of heat of hydrogenation. So this is the advantage. So overall, if I say heat of combustion is a more accurate data compared to heat of hydrogenation. That's why this is preferred. Okay, so this is the end of this discussion. So what we have learned today? We have learned today about the insights of heat of hydrogenation and combustion, little mechanism about this hydrogenation experiment, and finally with some graph we have understood what is the difference, how this thing occurring. So thank you for watching. Stay happy, stay blessed. See you in my next video. Bye bye.